talk from Dr. Peter Liu, and I'm just going to take a minute or two to tell you about our speaker this morning. So Dr. Peter Liu is a professor of chemistry at Bowling Green State University, and he's an Ohio eminent scholar. An eminent scholar is a distinguished research scientist that the university has recruited to initiate a major research program at Bowling Green State University. And his research combines chemistry tools and biology. And it's a very interesting and challenging area. And I know you're going to enjoy the program. So with that very, very short introduction, I'm going to pass it to Peter Liu.
So glad to be here, and it's very interesting. Seems every time you come here, we mark this day, the snowing day. I really appreciate you come this early and with the road condition. And how many students come from Bowling Green? Oh, majority of students from outside Bowling Green. Let me tell you a little bit about myself. And I got my PhD degree from Columbia University, and then I move on to trying to combine the biology and chemistry together. I worked for 11 years at a national laboratory in Pacific Northwest National Laboratory in Washington. Then by 2006, I moved to Bowling Green. I really enjoyed teaching and doing research here. And today I'm going to talk to you about something, how do we study molecules? We know in chemistry and everything's zoomed down to molecules. We try to understand those molecular property of those in life system, in material, in environment, in nature, and we know they're very, very small. We typically don't see them, and so it's very clear if you remember in your first day in class, if you study anything related to understanding of a molecular level understanding of those problems, the teacher will hold a molecular model in front of you to show you how this molecule moves. That's how, in the end, the whole property will build up from the material and
I give up.
Let's just leave it like this. Should be okay. So we want to see it. We want to play with it. So now this is possible. So today I'm going to talk to you how we be able to see a single molecule and monitor its behavior. So we all have probably had a chance to watch the horse racing. How many students think the horse, when it's running very fast, actually has some moment completely the horse is in the air, it's not touching the ground? How many students think such a moment can be possible? And how many students think this horse always has one leg on ground, even it's running very fast? Yes? So this question, many years, maybe 100 years ago, people all using horse, they wonder, what is this exactly when it's running very fast and how it looks like? So seeing is believing, so you will take a more picture and movie and then see, oh, actually, yes, there's a certain moment that's completely flowing there. And that's really a definitive proof. So in this nature world, and all those plants, animal cells, and bacteria, all formed by those biological cells in the units. And you can see those cells either in the plant, like the leaves or a tree, and all our human body, those bacteria bacteria, those cells, all the bacteria, they're very complex. They're very small. They may just 1,000th of size of your hair thickness. If you think your hair is very thin, but if you squeeze down, it's 1,000th times smaller, thinner, and that's probably the size of those living cells. And if you zoom in to those living cells, there's a whole world there. There's a nuclear and different components in the cell, and there are lots of different molecules in it, like proteins. And proteins has a different type of protein. They do different function and different time and different location. So it's very complex. Many years ago, about 100 years ago, and like this 1783. It's about 100 years ago, and this German scientist developed this microscope. And before this microscope developed, all the medicine disease studies all by experience. And once this microscope technology developed, they can see, oh, gee, even the leaf, the single tissue of your skin, when you zoom in, you see there's a whole different world. Those molecular cells in it, they structured this whole our body. And those technique has been further developed in recent years, getting more and more fancier. And so you can see, but the principal concept is still the same. And with a microscope object, and have a very large amplification to really zoom in to see those detailed structure. And that time, over the 100 years, we still cannot see single molecules, because molecules are way smaller, maybe millions of times even smaller. And now the technology development combined in recent 10 or 20 years or 30 years, we see this explosion of the technology. And now everybody holds a cell phone. And there's a cell phone, a simple camera there. Those small camera was like 30 or 50 years ago. Those small camera could be very fancy technology, very expensive, but now everybody can hold one in your hand. And also computer technology developed. Before it has to hold the whole room of the size of a computer. Now can be done a small computer chip. And so all those development now make this possible, combined with the different laser lights technology. Combined, now we can really see a single molecular and to really measure those molecules. And in our lab, we also combine not just using the microscope, also combine different technology with it, or homemade setup. And if you look at it from this side, it will be looks like very complex. And we put all those technology. Now we can really see, for example, a protein, and we'll see the topography, the shape of the protein, and watching it move around, and watching it make those changes, functions, and while it's under real action. So, one of the example you can see, this is one of the single molecular fluorescence imaging. Fluorescence is once you use the light to heat a molecule, the molecule can give out some photon, and by seeing that photon, we'll have an image, can see it. It's if you really see this through the microscope, most time using very sensitive camera. But if you train your eye to really sensitive to those very dark field looking into it, those single molecular looks like a twinkle star in the sky. It's very far away, looks, and blinking, little bit of blinking. And
those molecular actually is not like when we shine a light to the table. We see the image of the table. This table is very stable, right? Because there are many millions or billions of molecules there. But if you really zoom into each single molecule, they come out the light. It's not stable. They are blinking. Why they are blinking? Because it's just like a real individual complex object they see in the local environment is changing. When we put these tables here, it looks very stable. But under room temperature and this temperature, we are moving around, the molecules also moving around. But in such a small scale when they're moving around. And those motions is one of the reasons of their lights coming out like a twinkle star, blinking. So now we can really, through the microscope, we can really see those molecules give out fluorescence, have those imaging. Then we can study them. Here I give you a little bit of an example in early on in 1997. This work, those molecules are just a dye molecule. Dye molecule is just a color. When we see the blue color or orange color, different colors because there's a different organic molecule there. They absorb the photon, they give out different color. So we put one of those color molecule on glass surface, then very diluted. Each molecule will be farther away that we can really see them at one time. This dimension from here is very small. It's anti-molecular level. It's like a few micron. A few micron is 1 millimeter is this small. 1 micron is 1,000th smaller than 1 millimeter. This is just a few micron range. We see a few molecules on glass surface. And it looks like a small mountains because we detect the signal is to see in the emitted photon image, optical image. And when we measure the emission spectrum is what is the exactly color of those molecules. And here, the peak here, that's one color. And if this peak move around, that means this molecule actually, the colors keep changing. And can we imagine this a larger object? If you have billions of molecules, millions of molecules all together, this color come out is not changing. But once you zoom in, it will start to fluctuate, change. And this fluctuation, we can record it. And this fluctuation turns out to be very very sensitive, reporting this molecular and surface moving around, interact with the local environment. And that is very useful because in this way we can study biological molecular and the molecule in our living cell and how they interact with different components, with different medicine when we put it in, under a different disease condition, how they move around. Now we can really study them. So, for example, this is one work we demonstrated. We're trying to study the DNA damage. How come in our body, it's typically every single cell, every day, you have about 500,000 of the DNA damage repaired. And this repairment in our body really maintain that we don't have a genetic disease. We don't have disease. So it's really maintained very efficient. And the question is, how can in our bodies this mechanism can so effective recognize the problem and repair it? And there are some special proteins. Those proteins are very sensitive. They're moving around, they're looking around those newly synthesized DNA in our body. You know, our bodies continuously develop new cell, 1, 2, 3 more, and split into more new cell. When they newly developed, some DNA was not copied right, something wrong. So those protein will identify what's wrong and then mark on it. When they binding on it, those protein, so-called DNA damage recognition protein, they binding on it, and they will recruit other protein to come in to repair it. This protein will leave. So from this work, we labeled a dye molecule to DNA. You put a organic molecule to DNA molecule, our natural molecule in our body, definitely it's a damage to the DNA. And then this protein will recognize it. Oh, there's a damage, and then mark on it. The significance of this work is, this work demonstrated this marking. It's not like previously people think it will just bind it on it. No, it is keep sensing it. Never tightly bind it on it. And never leave. Just keep sensing it. So in nature, this protein keeps sensing, here is a problem, and then the other repairing protein will come in to repair, this protein will leave. And it's almost like you do fly fishing. Once you're fishing, you keep casting to that point, but never really bind to it. And mark it on it, and the other protein will come in. This kind of a fluctuation, those motion, you can imagine. If we measure one, because they all randomly fluctuate. They're not like hundreds of those XPA in a cell, they all go together. No, they just randomly fluctuate. They do this thermal fluctuation. And if you have thousands of them all together, if we do measurement, then this fluctuation, some on, some off, your received information will not contain this kind of motion. It will be averaging out, some on, some off, so it looks like an averaging static picture. So now we are capable to really see those important biological processes. The nature, previously, people cannot really tell if those recognition is like this. And people often been puzzled. Many of those recognition proteins, they are not very structured well. It looks like a very floppy. And why this is so powerful, effective, smart protein is not have very integrity of a good conformation or structure, but why it's so floppy? Because it's floppy, it's like a fly fishing, it keeps sensing on it and never tightly binding. So this work really demonstrated the usefulness of study one molecule at a time. Which is obtain the information, then our conventionally study millions or billions of molecules at a time. Day by day, when we're watching anything, we actually at the molecular level, we really study multiple molecules at the same time. But when we zoom in, we learn something important, such as this system is important for those biological function. Here's another work. This work also early on in this field development. It's an enzyme. You know, in our body, many of those biological processes is all through those enzymes to speed it up. When you drink milk, and your specific enzyme will consume this, will support you to consume this milk. And those enzymes working in our body all the time. And in this work, we studied cholesterol. You know, cholesterol, seems we all talk about this. Cholesterol in our blood is very significant. And this enzyme can convert cholesterol from one state, make it oxidized. This is a cholesterol oxidase enzyme. This enzyme, interesting is this enzyme, the center part is also a colored molecule. This molecule, very interesting. When it's oxidized, this enzyme itself will be reduced. And once reduced, this color molecule will turn to be dark, not give lights anymore. So by studying this enzymatic reaction, we can really observing the product one molecule at a time by converting from one state, oxidize it, the enzyme itself reduced. Once reduced, it's becoming to be dark. And then oxygen will re-oxidize this reduced state, coming back. So this enzyme actually like a pump. One turn converted one cholesterol from reduced state to oxidized state. And the oxygen will bring this enzyme to the initial state. Then this enzyme will go turn again. So this enzyme, actually, when we're watching this enzyme, it sort of seems that there's a color center. This color center will be giving out of lights and then dark, and then coming back to lights again, and then dark. So when we really observing those single molecular, gets the imaging, then we focus our laser on it, try to study this enzymatic reaction, and we see this, here is a bright state, here's dark state. We see it keep fluctuate, bright, dark, bright, dark, bright, dark. And what's happening there is a real single chemical reaction, the cholesterol being oxidized from reduced state to oxidized state. And so this, we can really observing those chemical reaction to understand how those complex chemical reaction occur. Why do we have to study single molecular? It's just like we ask a question, well, we have about 100 students here. Why do we have each student will have follow each student to understand for your whole day? For example, today, where have you been, what have you done, and what time, what location, which is a very important information and different from a snapshot. Oh, you're all here, you're all in this picture. So this in nature will, in terms of scientific research, this type of question come up again and again. For example, like a jellyfish. Well, the jellyfish in ocean sometimes could be thousands of, tens of thousands of them. But you're also wondering, what if I study one? Just watching one jellyfish and see how it's move and how those tails move. And we know this jellyfish is going to give us some information which is different from another one. And also will be different from if we study two altogether. The information is important because this biological system is more complex. And which is, if you go to study many, many jellyfish at a time, the information is all consistent. They are not contradictory, but they're complementary. And the single molecular approach compared to conventional approach, we study many molecules at a time. It's almost like we study one jellyfish at a time and we record it, those function, where it goes, what it do, and to understand it. And then combine it with our conventional way of study. You fly very high to see underneath, you see thousands of them, you take a picture, and these two information put together will give us really good understanding of what's the nature of jellyfish and how it lives and how it functions. The same thing for moleculars, especially proteins, those biological molecules. They're all very complex. They will all move around. They never stop moving. When we see something like a biology, it's just like a biological cell or those things. It looks like it stay there, but in molecular level, they all constantly move. And they move, they don't really coherent with each other. Some move this way, some move that way. They're all independent, fluctuate. So to study one at a time really contain some significant advantage. So here I'm showing you one example. This example is something related to our brain. And we keep saying, thinking, we keep showing this figure. But turns out that it's really happening in brain. Some of those proteins in the thinking process will involve rotation. And it is this protein. It will just simply rotate it. You can see it's like outside there are a surrounding ring, and there's a center there, this protein. And you can imagine when those proteins are rotating, they're all independent. Some rotating left, some rotating right, and some rotating faster, some rotating slow. And are they really rotating? And if you really take a tissue of the brain, you cannot tell the protein is really doing rotating. And so for many years, people has been hypothesized those proteins called motor protein, like our car, the motor is rotating. But there's no way to prove it. Furthermore, there's no way to study it. So single molecular spectroscopy approach will be able to zoom in to really see it. You can really see it. It's really rotating and sometimes coming back, sometimes forward, and it's really rotating. And people have done very detailed study. They found out one of the striking things. This rotating protein, the motor, the energy efficiency is 100%. Once it consumes some chemical energy, it will convert it to rotating motion 100%. Or our machine, if our machine can reach 100% efficiency, then all the energy consumption will be significantly lower. And so, like this example, it's using those techniques, not only just observing those biological molecules, but you can also manipulate those molecules. For example, in this case, it's a organic strain type of molecule. And using this technique, you can really holding the two ends of this string and tie a knot on it. So they just show the power of those approach. You can really holding it and tie a knot on it. So here's one example. Maybe in the end you can see they softly rotating, and then it looks like a little blurred because it's a little bit lifting up out of the focus of the optical imaging. And then they tie the knots. And in the end, it looks like the knot is too tight, then this string was broken. So here's another example. They tie the knots of the DNA molecule. DNA is a linear molecule, so they can really tighten knots. But imagine if they can tighten a knot, they can do many, many things. Manipulate the conformation and bring it to a different location and introduce a specific local environment. So those can all be done right now. So let me give you another example of in nature, it's very important. It's all those leaves, when they fall down, they will be degraded. And right now, we all heard about renewable energy, clean energy. One of the major renewable energy is a bio-renewable energy. If imagine each year, all those leaves fall down to the ground, we collect them, and then we convert them to energy, then that will be useful. To convert them to energy, one of the first processes is to break down those cell walls. Those leaves, they don't like to degrade very fast. We want them degrade very fast under control. To do that, this enzyme called lysosome, T4 lysosome, is an enzyme that can do this. This enzyme has two domains linked by this like a spring type of linker. This enzyme basically just do those so-called hinge bending motion to cut this cell wall. It's a polymer sugar. it's a linked, many sugar molecular linked chain. That's the major components of the leaf cell wall. So this enzyme can cut it, almost like we play the game like a Pac-Man. It's a chewing. But again, who has ever really observed this molecule doing this Pac-Man motion? Well, now this is possible. So we can label a probe molecule on each side. This probe molecule will give out a signal when this motion occurred. We'll be able to probe this motion of this conformational change. So I will directly go to show you data. So if we tester those protein to the glass surface, then we can imaging them. The shape, this looks like a spike, but this is just optical signal telling us there's a protein which has been labeled by those optical probes. And then we can focus on one protein at a time to follow those motions. And what is the motion we are following? You haven't studied chemistry yet, but it is this cell wall is the protein is a molecular chain, all linked by this by those here this showing oxygen, those linked together, and those chains should be cut off. Then that's how the cell will degrade in nature. And involved this is this protein will open up to let this chain diffuse into this active site of the reaction, and then close down to react. What's react? It will be cut this chain, and then each side of this product will diffuse out. So for enzymatic reaction, each turn you will be open up and close down, bind it on this polymer chain, and then cut it, just like a Pac-Man. Cut it. Like a Caesar, you cut it, then each chain will, the product will leave. And then we'll open up, cut again. So we'll be able to show you that we can measure this, process. To open up, initially this is just a portion of the chain. This enzyme will be open up to let this chain to bind it to it, and then close down to really form the good binding. Bite on it, and then cut. So this is the process we probe. And here, when we probe it, this is the time when we watch it. And here, the higher signal is open. The lower signal is closed. And we can really see it's open, close, the change. But here you can see the signal is very noisy, very weak signal. Looks like all random noise, but you can zoom in to anywhere. For example, here looks like a lot of noise, but you zoom in, you can really see this open, close motion. So for each open, close, it's a open up, binding down, close down, cut, each cut, just like Caesars or Pac-Man. Each cut, we can really monitor this process. And this protein actually, you can see the active site is empty. There's really a doorway, need to be opened up to have a substrate go in. And here we calculated this charge, electro charge. We know the electro charge, the positive charge, like to interact with negative charge. And exactly this enzyme doing the same thing. This enzyme, very interesting. The front of this enzyme is positive charge, and the back is negative charged. So if you calculate this substrate, this is just portion of this polymer chain. It's negative charge. So nature has this enzyme function over the years evolution. It's very smart. This enzyme has a positive charge front, always approaching the substrate because the substrate, this polymer chain, sugar chain is negative charge. So you always approaching this substrate from front, open up and close down. So never turn the back to it because the back is the same charge, so they're repulsion. So in this work, we can really see those kind of motions. For example, here we can really see those kind of motion. The substrate go in, and the substrate go in. It's open up. And we can really see those process. So in recent years, there are additional development in the single molecular spectroscopy, which is beyond just observing it. Single molecular spectroscopy can also manipulate those molecules. So it's just like we have developed those molecular finger to hold the molecule and to change it, and then study it. It has a different function. So, for example, those molecular could be very structured. Then we try to, with this molecular finger, to come in to really manipulate the structure and see how the function change. So those all can be done. And we can also study in the biological system different protein interaction. We can bring them together and see how they interact with each other, have a certain function. So those are all could be very important. With those techniques, we can really see those molecules. For example, this is just a piece of a DNA molecule. So you can really clearly see this DNA molecule is a string like a linear molecule. We can see a different shape. And another application I like to briefly mention is this technique can apply to understand, for example, how a nerve signal passing around in our brain and in our body. And we know in brain, all those signals go through those nerves and passing through each other, and that's how we do our thinking. And how those electronic sparks go through the brain. What is really happening? What is really happening is all those strings, those nerve fibers, actually they have a lot of small channels, proteins on the surface, so-called ion channel, or they can release a charged molecule in and out, let them in and out. And those ion channel actually is open close along your nerve cell, and that's give you the electric signal passing through back and forth. So right now we can really probing those channel open close and see their charged particle go in and out to see this nerve signal passing by, and also know how those open close really happen of this protein. So for example, we can see the current signal open, close, simultaneously have optical imaging to really watching those detailed open close. And those are all really can facilitate our understanding of a nerve signal and brain functions. Recently, there's one example where we study flu. You got cold, right? What is this kind of a flu? It's because of a virus get into your cell. You are infected by flu virus. And the question is, how does flu virus get into your cell? If we know, then we can develop medicine to block it. So the first thing is we have to see it, how it's get into our cell. So in this imaging, you can see this flu virus. You can really watching each one of them. Those are squeezed trajectory is actually by a whole movie. They condense into those one figure. They see one of the virus seems to move around the outside of this cell, never get in, this one. But this one seems once attached to the cell wall, it's getting very effectively go in. And you can see this purple one is getting in and really moving into the cell. And there's this one, red color one. This one seems just moving around the cell, never get in. So by watching all those, and people now have better understanding how those virus infect our cell and how it's moved in and from where and through what channels. And then we can develop a medicine to say, let's block it. Let's, then that's related to very critical understand how do we prevent such disease. Another example is recently we have those technology development. When you got sick, you take some medicine, right? And for example, sometimes people got cancer. And cancer is just the same cell in our body, but it's developed out of control. And once you take a medicine, simply traditional medicine, those medicine, if it's attack the cancer cell, it may also attack your health cell. So one of the really research frontier would be, can we make the medicine like missiles? They can recognize the cancer cell, only attack cancer cell. So people will now have, through this imaging research, really try to understand how can we develop a medicine to understand how can we make them to be effectively only go into the cancer cell, not go into the health cell. Those things, without imaging, people has been developed medicine, developed a way to deliver medicine many, many years by experience. They don't know why they developed this current formula. It could be only have 14% go into the cancer cell. And most of them just wash away. And how can they improve it from 14% to 40%? They say, we need to know the real nature, how those medicine get into the cancer cell and not get into the health cell. By doing that, you really have to observing it. So I think I will finish my talk just by one example. What I'm trying to say is the single molecular spectroscopy study complex molecular motions, biological function, actually has very profound impact to many, many different fields, include computation, next generation or future generation of computer. You can imagine this. One of the good examples in 90s, the IBM developed a very powerful computer called Deep Blue, very fast computer. And to demonstrate the power of the computer, they let this computer play chess with a chess master, a famous international chess master. And they have many, many wrong. And sometimes the computer win, and sometimes the chess master win, and sometimes tie. Looks like a very comparable. This computer is really powerful, can do all those logical thinking. And that is good. But after all those match, development, excitement, the people ask a simple question. Well, do you know how much energy consumed by this computer to play those match? Aha, oh, they calculate. The electricity they consume maybe gigawatts, a lot with power, energy. And they say, how much energy consumed by this master while they play chess? They probably just consume by a cup of milk. And then the question is, how can a human brain, such powerful, such energy efficient, and competing with this machine, although it's very advanced, now it's, and our time is the most advanced computer, most smart machine. Why? Because the people think it's because our brain has all those molecular they don't take a lot of energy. They just take a room temperature. Just like us, a stretching arm, and we don't take a lot of energy. Those smaller proteins just open up, close, open, close, and fluctuate there. And many, many of them. And they form the whole system. They fluctuate, make a decision, make a signal go, and very powerful. And this really pointed to a direction. And right now, many countries are moving to this direction, which is beyond our computer. Right now, our computers are, okay, we make it more powerful, more small. But the way you're doing those computer thinking has to be revolutionized to understand those single molecular, how they move, how they do those thinking collectively. If we understand that, our next generation computer will be much more powerful, because right now people say the current track of the computation power is keep being powerful and powerful and involve many aspects of our life. It's not sustainable energetically, because people estimated by 2050, if the computer developed this way, many of the things are all computer controlled, our energy, 50% of our energy will be used to drive those computers. That clearly point out this is something need to be fundamentally changed. Let's learn from nature, from our brain, and from those small molecules. So let me summarize. We all know that many years ago in the San Diego Zoo, there's a small panda was born, and many people got a chance to see, or through web to see. Very interesting. You can see the small panda grow initially very small and grow more and more personality, finally grow up. This is almost like a single molecular experiment. Those biological molecules are complex. You study one at a time, you monitor it, follow it, you learn a lot more. Then you study the many of them all together, you take a shot. They are consistent, complementary, but they provide vital contribution to really understand those complex systems. So in summary, I will say, number one is single molecular spectroscopy. It's really powerful to study complex biological molecules and biological functions. And number two, those kind of study obtain the information often not obtainable from our conventional way of study those complex life systems. And number three is those techniques not just for those type of a problem. The implication and further application can be extended to very broad field. And in your life, you will be the future of the country and the science, and you will see the knowledge developed here can be applied to very different field which we cannot even imagine at this time. And thank you for your attention. If you have any question, please ask.
Thank you very much, Dr. Liu. So this morning we've learned that you can learn an awful lot by looking at very, very tiny things. And those tiny things are moving on us. So I'm sure there's some questions you would like to ask Dr. Liu, so if you raise your hand, I will come over to you and you can ask your question, okay? Start here.
Around the middle of the program, you were talking about how you can't have one molecule facing another one in a certain way. I wasn't quite understanding that.
So how a single molecule involved chemical reaction? Yeah, so we know all the molecular in nature, those chemical reactions are occurring in our biological body. That's occurring all the time. But the question is, conventional way study is from like study skin, or even very fancy technology can zoom down to study the cell level. But because of the living cell is very, very complex. For example, it's a very detailed, many structure there. And those conventional way will be not so powerful to study how this particular biological function occurred at a particular size. So you will need to zoom in to really see it. So single molecular spectroscopy will bring such a capability to be able to zoom in to a specific size to understand specific chemical reaction. And then combine with the overall study, we'll have the whole picture. That's how this technique approach trying to do.
I forgot mine.
Okay.
How many atoms will it take to make a molecule?
Oh, it could be hundreds of thousands of atoms for those biological molecular. Those biological molecular could be 20,000, 30,000 of the atoms built together for one molecular. So you can see all those atoms linked by chemical bond. They're all flexible. So all those molecular, they have their own will, their own life. They don't listen to each other. So now we're trying to really treat them as an individual. Very early on, when this technique developed, and some people publish the paper or give presentation, they will give a name of a molecular 1, molecular 2, and they all have a different behavior. Yes.
What does manipulating mean?
Molecular means one of the building block.
What does manipulating mean?
Oh, manipulate a molecular. Manipulate means you can hold a molecular and change it by your will. If you like to change it this way, you can move it this way. So when you manipulate it, you can really operate it on it. It's such like a surgeon to operate it on something. You can play with it, not just observing. So beyond just look at it, you can now start to tweak it and to operate on it.
Are molecules made of matter?
Yes. Molecular is one form of matter at a certain level. Molecular is made of atom. Atom is made by nuclear and some other particles. Those all matters. And those molecular will aggregate together, made up this matter. This is made by molecular, just different type of molecular and different way they put together. So chemistry, if you got a chance later on to study chemistry, actually chemistry is really hold to study this fundamental building block of this whole world. And the molecular has many different types. Just like our color, you can see today we have many different color. And the reason your clothing has different color because your clothing was containing a different color molecule. Yes.
How many nanometers in length are a molecule?
How many what? Oh, how many nanometers of molecule? So nanometer, nano. Now we heard a lot. Nano this, nano that, and even we heard about nano car, right? The car very few consuming, we call it nano car. Nano is a dimension. It's a dimension. Typically, a biological molecule will have 1 nanometer to 10 nanometer to 20 nanometer in that range.
How much smaller is a nanometer than a millimeter?
Oh, if a millimeter is this much, and you can shrink it down by 1,000 times, then that's still 1,000 times need shrink down to the nanometer. So you have to shrink it down by millions of times to nanometer. And that's why we cannot see it. We can see millimeter, we can see our hair, but if you shrink down by millions of times, we cannot see. But once now this technology, we can zoom in to see it and the specific location. And all we see is all very stunning. The world is moving, it's all moving there. And they do actions. And previously, we understand this world is by averaging. When our technique measure, all the time we measure millions of molecules at a time because the molecules are too small. Yes.
Are molecules in everything or just some things?
Molecules is one of the form of material. Well, we can see the whole universe was formed by atom. And the atom is not necessarily from molecules. On Earth, our environments facilitate those atoms form the molecule. That's how life starts showing up. And on Earth, almost any of those existing material is in the form of molecular. They build up differently by different molecular. They're changing, those building up changing with temperature. Like the Lake Erie, during the summer, we can swim on it. And it's liquid. During the winter, it's solid, it's ice. And so the molecule are doing all those magic things. And the question is, are they very uniform? No, that's a spectacular world. They all have many, many different molecular, different way to form different shape. So now we can really study them in great detail. Yes.
Are we able to see atoms?
Yes, we are able to see atoms. Those techniques, I didn't have time to talk about that. We're not only able to see atoms, for example, some technique you can really see, you put some gold atoms on surface. You can see those atoms there. Not only that, you can bring those gold atoms to form a chain, a gold wire. And you can also link those gold atoms to a molecule. So all those magic things, that's what we think we can do using our hand in our laboratory. Using the models, we can do. Now we can do in real world, yes.
How are atoms made?
How those atoms named?
How are atoms made?
Oh, atoms made by different particle, more basic particle, like electron, nuclear, and by different nuclear. Inside of a nuclear, they have a neutron, they have a different basic particle. So atoms is made by a more fundamental particle, even smaller.
What is the volume of a molecule?
The volume of a molecule is like, let's say, it's like if you have a milk, if you have 1 milliliter water, and if you go down to the molecules, the molecule could be like millions of trillions of times smaller than the 1 milliliter liquid. It's very, very small. You can imagine the dimension, if you imagine a cubic box. This dimension, each of this height, width, or length, it's about 1 millionth of times shorter, 1 millionth of times shorter than the millimeter. So if you have a small sand, like a millimeter cube, if you shrink by millions of times smaller, that's about the size of molecular.
Besides the lysozyme that breaks the chains, are there any other proteins that do that?
Yes. In nature, there are many, many proteins doing the work or break down those nature molecules. You can see the nature is very interesting. Nature, by over the years, developed this plants, these leaves. They form those polymer chains. They trying to protect from degrade. They don't want to be break. That's why we see a tree there come up a thunderstorm, the tree doesn't melt down, it stay there. And that's why we see the tree leaves fall down. It can stay there for many, many days, not change. They try to resist that. On the other hand, the nature also has those enzymes try to really attacking this, try to make them degrade. And not just one type, there are many different types. And those one type we studied is related to, we think it's enhance our understanding, how do we convert those nature plants to biofuel. The first step would be degrade them to small molecular, becoming to be our gasoline, we hope, in the eventually the product. Yes.
What is matter made of?
What is matter made? Matter made by all those particles, and matter has different forms. And right now, the whole Earth is a matter, and there's different forms of the matter. The matter can be go down from our, for example, our body, from skin, from bone, and go down to cells. And cells can be made by smaller aggregates of the molecules gathering together. And the molecules will be made by atom. Atom can also go down to electron and nuclear. And nuclear can also go down to those basic particles. And finally, there's always this debate. Is the matter can be continuously break down to the fundamental particle, and what is the final form? And this debate, I think, is still more physically. We see it can be go down to a certain level. It's will have a fundamental form, but it's still a very interesting debate.
Are some molecules and atoms dangerous?
Some of the molecules and the atoms are interesting.
Are some molecules dangerous?
Oh, yes. Some molecular, in nature, it's always, the whole universe will develop is very interesting. It's always like a feedback mechanism. You have something moving down, then you have something moving down, moving up, you have something moving down. So the whole universe is totally equilibrium in such equilibrium. And in terms of dangers, we'll say for human health, well, you can see some molecular could be dangerous. For example, when those molecules form like some type of virus, that could be dangerous, could make you sick. But on the other hand, your body can have a very similar molecule, can also change to be very different property. One of the very interesting effort in a pharmaceutical company is try to synthesize some nature medicine molecules. And it's very interesting. This molecule could be totally a good medicine, but if you're changing one chemical bond to another direction, then this molecule can be totally ineffective. Or if you change it around, it can be harm your health. Yes.
Okay, I think we should wrap it up here and give Dr. Peter Liu a resounding round of applause.
Yeah, I'm really enjoying working with you.
So let me take just a few minutes to tell you about activities this afternoon and challenges. One of the things that Dr. Liu has, I think, made very clear this morning is that there's a lot of work studying things at really, really small levels. So we're at university here, and we have a challenge for you. Are you up for a challenge? Yeah! Okay. Well, there is a challenge this afternoon. This afternoon we're going to see DNA. We saw pictures of it. You'll be able to see goobers of it. But the other thing, the other real hard challenge is that Dr. Liu studies microscopy at the molecular level, and the first step to do that is to do conventional microscopy, in which you look at cells. And this is a stylized cell, and it's a really clear picture. In school, when you're looking at real material, it's not that easy. It's tough. So there is a challenge today, and the first one of those challenges is to learn how to carefully use a microscope to actually visualize material. This is not easy. First-year university students, when they do this, forget all the time. You know why? They don't listen. They forget. I know, in fact, 40% of them fail the test. So I figure, how many fifth graders do we have here? So you're my challenge to university students, because I want to be able to say to them, are you smarter than a fifth grader? Okay? So that means that when the instructors tell you how to use, you be very, very careful. Because if you pass the microscope focusing test, we'll give you a certificate. But better than that, you see, I want to be able to say to all the first-year students, are you smarter than a fifth grader? Fifth graders could do this because they pay attention. So that will be one of the activities that we're doing this afternoon. And we're sort of looking at this level. And what you heard, and what's really interesting, is what's going on 1,000,000 times smaller than that. But we're going to have to take the first step so that you guys, 10 years from now, can follow in Dr. Liu's footsteps. So, our groups are going to take you to lunch. This afternoon we'll be at the Perry Fieldhouse, and you'll be there with your parents doing one of 15 activities. Have a great lunch. See you in an hour or so.